Here's some solutions you can correct your work with for the pigeonhole principle. The first one was from St. George. In a barrel, there are 50 marbles of various colours. Of these, 5 are green, 17 are blue, 12 are yellow, 12 are purple, and 4 are orange. So I've written that down to help me keep track of all the information. What is the least number of marbles that can be selected from the barrel to ensure that 7 of the selected marbles are of the same colour? I do like to think of the worst case scenario. We need 7 of one colour, so that can't be orange, for example, or green, because there's only 5 and 4 of those. The worst case is if I'd have all of them picked but never actually got to the 7th one in any colour. So that would mean 5 green, yes, but 6 blue, 6 yellow, 6 of the purple, and then 4 of the orange. When you add them all up, you get 27 marbles. That must mean the 28th marble, which could either be blue or yellow or purple, will give 7 of a colour. So basically, you need to pick 28 to guarantee that you get 7 of the same colour. The other way to do it, maybe not quite as logical, as only blue, yellow and purple can give 7, let's leave out the green and orange, and that gives you 41 marbles. I need some number of marbles to be selected and divide them by the 3 colours to be, by pigeonhole principle, greater than 6. So the number has to be bigger than 18. Remember, 18 divided by 3 is 6. But as soon as you go to 19 over 3, 6 and a third, so you would round up to 19. The way to use that 19 is to go back and add in, of course, the 5 green and the 4 orange to then give you 28. So not an easy question. North Sydney girls, their multiple choice question, 6. From the set of integers, 1 to 2, 3, 999, numbers are selected one at a time without repetition. So no order in particular, but one at a time. How many multiples of 9 are there? Out of the 999 divided by 9, there's 111 multiples of 9. So if we pick 888, we know that we won't have 111 multiples of 9. So in the worst case scenario, you pick all of those 888 non-multiples and then you include 4 multiples of 9 following that. That's the worst case scenario. So it's 892. Still in North Sydney, 12C, a 2-marker, an exam sat by 130 students was marked out of 25. No half marks were awarded and exactly 4 students scored full marks. A total of N students received the modal mark. What is the smallest value of N? And justify your answer. We know that 4 got 25, so we need to remove those, and that meant that there were 25 remaining possible marks from 0 to 24. The objects that we need to place into those spaces, there's 126 remaining students. So if you do 126 divided by 5, you get 5 lots of 25 plus 1, remembering that there were 25 marks. As there are more objects than 5 times the number of categories, at least one category must contain 6. And remember that the modal mark means the one that appeared more than anybody else. So at least one mark was awarded to at least 6 students. The other thing you could have done is divide that 126 by 5 using the pigeonhole principle and getting 6. I did like that they gave some good feedback for this paper, and they said many students believed that this was a statistics question and attempted normal distribution. So they didn't recognise that they had a pigeonhole principle question. And a number of students correctly divided 126 by 25 and rounded up and then added another one. And that notion of adding or rounding up is the pigeonhole principle. A majority of students did not correctly count the number of categories, so they forgot 0 as being a possible mark. Moving on over to Manly, you'll notice that for their HSC trial, the Pigeonhole principle is their first question. Nice way to ease them into the paper, huh? Each of the students in an athletics team is randomly allocated their own locker from a row of 100 lockers. What is the smallest number of students in the team that guarantees that 2 students are allocated consecutive lockers? So let's have a look at this question. If every student actually has a vacant locker next to them, so kind of thinking of that worst case scenario. So there's your bank of lockers. You put the first person in and leave a space. Put the next person in and leave a space. Put the next person in and leave a space all the way through those 100 lockers. That would mean you would have 50 students. So the very next person who goes in, no matter where they go in, will result in those 2 people having consecutive lockers, or one after the other, with no gap. So that means you'll have 51 students before you can guarantee that you'll have no spaces or consecutive students in lockers. A 3x3 grid is to be filled with numbers from the set -1, 0, 1. Prove that among the sums by rows, columns and diagonals, there are at least 2 of these sums equal. So we're talking about sums, so I think it's important to look at your sample space first and see what's actually possible. There are 7 possible sums. You could have 3 -1s, for example, or you could have +3 and all the whole numbers in between. So they're the pigeonholes, they're the sums that you could get. There are in fact 3 rows, 3 columns and 2 diagonals, so there's 8 calculations that will cover or go into those 7 possible sums. So they're the pigeons. The 8 divided by 7 with the pigeonhole principle, yes, I know it could be 1 and 1/7, but remember we round up to 2. So by the pigeonhole principle, at least 2 calculations will be the sum. Show that if 100 unique numbers are in a set, then at least 17 of them will have the same remainder when divided by 6. So I guess the first question is, well, what are the possible remainders that you could have? There are 6. You could get no remainders, or 1, or 2, or 3, or 4, or 5. So if you do the 100 divided by the number of remainders, then I don't think you get exactly 17, but when you use the pigeonhole principle, you do. Thus, by the pigeonhole principle, there are at least 17 numbers with the same remainder when divided by 6. Some good feedback again that the teachers from this school gave. Most students have not justified their answer. Some students were weak in applying the pigeonhole principle and then did not mention all the possible remainders. I can see that 0 would be an easy one for people to forget. But I hope you're seeing a trend in the way that teachers are wanting to see the answers being left and in the way that the questions are written too. Alright, Mr. Howard wants all students in his class to have the same birthday. The course must have no less than 30 students. And what is the minimum number of students required for Mr. Howard to form a class of students who all share the same birthday? I think we had something like this similar in our class examples, where to make sure that you have a repetition, you've got to make sure you cover all the days. So they've gone 365 times 30 and then added 1 for that, making sure that next person would definitely mean you have the double up. A private institution course regulation requires that the same number of students achieve each grade from A to E where possible. What is the smallest number of students required to ensure at least one particular grade is awarded 7 times? So how many students are we after? Well, there's 5 grades from A to E. At least one grade awarded 7 times implies that each group, as worst case scenario, would at least 6. So your 5 times 6 for your 5 grades plus 1 is your 31. Given that n students are to be placed into 4 classrooms, what is the minimum number of students to guarantee that there are at least 2 students born in the same month in each of the 4 classrooms? Birthdays again. I got this wrong the first time I did it because I took it as doubling birthdays, not months. So I underlined that because I made a mistake with it. The worst case scenario is in each room there are 12 students, all born in different months. By the Pigeonhole principle, 1 more student in each classroom would guarantee that there are at least 2 students in each classroom who are born in the same month. So we need to multiply 4 by 13 to get to 52. Hopefully that'll give you a really comprehensive feel for what exam questions are like.